So this time we've got a ball thrown directly upwards at 20 meters per second. And it's thrown upwards from a height of 2.5 meters above the ground. And so let's just mark that on, just doing a bit of a sketch of what the problem is. And then actually I can just do it like this maybe. Just move this out the way. Just move this out the way. And so we'll just put this as S, as our displacement, and we'll have displacement positive upwards. And we'll have zero displacements at ground level. And so that's our displacement this way, and it's starting at 2.5 meters above ground level. Now, what gravity does to things is it's 9.81 meters per second squared. So basically, gravity, the acceleration is always acting downwards. So if something is initially going upwards, so it'll go with high speed, it'll slow down because it's going in the opposite way from the direction of the acceleration. So it's going to start with a reasonably high speed. It's going to slow down because acceleration is acting downwards, and then it's going to start going in the same direction as the acceleration, so it's going to speed up. So it's going to look something like that, except it's going to hit the ground. It's not going to go past the ground. So this acceleration, so when you've got acceleration acting on an object, if the velocity is in the opposite direction from the acceleration, and we could even write that on here, we could write this is the velocity is 20 meters per second. So initial velocity is 20 meters per second. And we could also show the acceleration. Might want to use a different color for that. And so acceleration is downwards and always under gravity, 9.81 meters per second squared. So when the acceleration is in the same direction as the velocity, that means this object will be speeding up. But in this case, the acceleration is in the opposite direction, so it starts off and that's going to slow down, but then it's going to go in the opposite direction, and now the velocity is in the same direction as acceleration, so it's going to be speeding up on the way back down, which is what you expect for a ball. So the first part of this question is asking us, what's the maximum height the ball will reach? Well, we know at its maximum height, so let's just start writing some of this down. At max height, the velocity is going to be 0. So when this ball, let's just grab this ball again. So when it gets to that point of maximum height, that's the point where it's just changing direction. And so it's going from positive velocity to a negative velocity. Therefore, the velocity at that highest point is going to be equal to 0. And we're asking, what's the maximum height? So it's the distance we want. And so it's going to be this equation here that we're going to use. So we're going to know that the velocity we're interested in is going to be 0. And then we know the initial velocity is 20. We know the acceleration. It's minus 9.81 meters per second squared in this case. So I'm doing this upwards as positive. The acceleration is acting downwards. The Earth's gravity is accelerating things downwards. We know that initial displacement, 2.5 meters above the ground, taking everything relative to the ground. And we're trying to find out this distance S, where this velocity is 0, which will be the maximum height. So let's have a go at that. So the velocity, our max height velocity equals 0. We also know A0 is equal to minus 9.81 meters per second squared. That's how things accelerate in gravity. And we know that S0 is equal to 2.5 meters. We'll keep everything in meters and seconds. So therefore, we're going to have the velocity squared at a given distance is just equal to initial velocity squared plus 2 times the acceleration, which is constant for all of this theory. Acceleration has to be constant. Distance minus the initial displacement. Sorry, displacement minus initial displacement. So v squared at a given distance s is just equal to So our V naught, oh, I haven't written that down, and V naught was equal to 20 meters per second in the positive direction. It's going to be 20 squared plus 2 times 9.81 times 2.5, sorry, the distance is what we're trying to figure out. Distance minus initial displacement was minus 2.5. And we knew that that final velocity, the velocity we're looking for, is going to be 0. So therefore, because it stopped at the maximum height, it's going to have 0 velocity. Let's just start figuring some of this stuff out. That's going to be 1a squared is 400 plus, so we're going to multiply out these brackets now. So we're going to have 2 times 9.81, which is 19.62 times s. 19.62s, take away, so we've got a negative there, this is positive, so this is going to be negative, so it's going to be 19.62, 2 times 9.81 times minus 2.5. So that's going to work out as 2.5 times 19.62. It's 49.05. Therefore, we're going to have 19.62 s is going to be equal to 400 minus 49.05. It's 350.95. So s is going to be, divide both sides by 19.62. Going to be 17.88 meters. So throwing that ball pretty hard, which it is, 20 meters per second is pretty fast. Be a bit too fast for someone throwing it, maybe they've shot it out in a cannon or something like that. So max height above ground level, and there is a quick way out in ground level for engineers. You can do it like this. Above ground level, so it's a G and an L kind of crossed over each other, is equal to 17.88 meters, which is fair enough. I'll just change that to 17.9 meters, these significant figures for the answer. Now, this second part is asking if the person who threw the ball moves out of the way, how long will the ball hit the ground? Now, bear in mind, this is all one stage. Even though this ball goes up and then comes back down, it's all a single stage. The acceleration acting on the object is always 9.81 meters per second squared downwards. So even though it's changing direction, it's still a one stage. The acceleration is constant throughout this whole process, even though the velocity is changing. Now, this next part of the question, it wants to know if the person moves out of the way, how long will it be before the ball hits the ground? So we're probably looking at one of these formulae with time in it. And we have a couple of those. So we've got ST, so we've got this one here. We could use that because we could use that. That one would work. And so we're trying to find out when the displacement is going to be back to 0. And so we can use this equation here. And we're going to figure out when this ball gets back down to 0. That would work. I'm just trying to think if I could use any of the others. We might be able to use that, but not really. So we don't really know the velocity when this thing hits the ground because it's going to be accelerating that whole way down. So it's going to have some non-zero velocity when it gets to there. And so that's not going to do. So let's just use this one here and see what that gives us. And so this is one of these. This is why we learned how to do parabolic equations, or why I revised, I summarized, or reminded you of how to do parabolic equations. And so we've got S, the displacement at time t is equal to, for constant acceleration, S naught plus V naught times t plus a half acceleration, which is just a constant value, half at squared. So what do we know here? So we're trying to find a time at which the displacement is zero. So we're taking displacement relative to the ground. So at this point, the displacement is zero. So we're trying to find a time at which that is equal to zero. Is going to be equal to, our initial displacement was 2.5 meters. Then we have plus, and the initial velocity was 20 meters per second. So 20 times t plus half a naught t squared. Oh, sorry, we know a naught, so we can put that in. So a naught is equal to half times 9.81 times t squared. But that acceleration is in the negative direction. So this whole thing is going to be negative. So now we want to get this in the form, you remember we're talking about the quadratic is of the form ax squared plus bx plus c equals 0 to solve it using the formula we know, whereas x could be any, these a, b and c are just numbers, and x is just any variable, could be x, could be t, in our case it's t. So let's arrange this in the right order. So we've got minus, let's figure that out, half times 9.81, 0.5 is equal to 4.905. So we've got minus 4 point, I'll just keep 4 significant figures if we're going to be using it again. So minus 4.905 t squared plus 20t plus 2.5 is equal to 0. And I'm just swapping sides there, so I'm swapping these two sides around, and so that's all good. I could times that by a negative, but there's no point. I've got two positives there anyway. So now we're thinking to ourselves, so what's A, B, and C? So A is equal to minus 4.905, B is equal to 20, and C is equal to 2.5. So we've got things in the right order. We've got the variable squared, and then the variable, then just the number. And we are making sure that we take the negative with this one. And so therefore we've got the A, B, and C we need. The first thing we figure out, might as well just do it over here, is square root b squared minus 4ac, which is equal to square root 20 squared, and it's got a negative, so it's going to be plus 4.905 times, I've lost my 4, b squared minus 4ac, and so it's going to end up being positive because that a is negative, so plus 4 times a 4.905 times c 2.5, and just figure that out. It's 21.19. So that's what that equals. And so then we use our formula. So the solution of this is going to be t, because it's not x, it's a t this time, negative b plus or minus square root b squared minus 4ac all upon 2a, which is going to be minus 20 plus 21.19 over minus 2 times 4.905, so just taking the negative out to the front. So we just do the two solutions, that's okay. And so that's one solution, is where you're adding, or we could say or. So let's just say T1 equals that, and T2 is going to be minus 20 negative b minus square, oh, I don't need to write that, we've already calculated it, minus 21.19 divided by minus 2 times 4.905. And then we'll just figure those out. Just give me a second, I'll come right. Okay, so I've just calculated those and kept them to 4 significant figures for just now. And so what we can see is we've got one answer, T1 is a negative 0.1213 seconds, and another one, the time is 4.199 seconds. Now, when you're doing these problems with quadratic, or this is, quadratic equations in them, and you get the two answers, you've got to think about which answer is sensible. It might be both of them are sensible, but in this case, we're looking at a negative time, so it's like you're going backwards in time to get this answer. And so, and that is not possible for us. What we are interested in is when it's going to hit the ground after you've chucked it, not before you've chucked it. It doesn't even exist before you've chucked it. These equations weren't true before you threw that, because before you threw it, the acceleration was 0. The equations we're looking at are for the stage of this motion where the acceleration is 9.81 meters per second squared. Okay, so this answer is meaningless in our context. This is the answer we're interested in. And so that's the answer we're looking for. So, nope, don't know what I'm saying. So, ball will hit the ground after 4.20 really, 4.20 seconds to 3 significant figures. Just double check what we were asking. Yeah, sort of person's moved out the way so it doesn't hit them on the head. That's all the question was saying. Now, does that make sense? I think it does, but what we could do is, just as a quick check, we could take this value and stick it back in the equation, make sure we haven't made any mistakes. And so displacement at time t is just going to be displacement at time 0. This is just a check. Which was 2 meters, 2.5 meters, 2.5 meters plus the velocity at time 0 was 20 times the time, 4.199. And then it's minus a half times 9.81 times 4.199 squared. Let me just figure that out. It's equal to 0.003, which is good enough given rounding errors. Okay, so it looks like it's okay. That's us answered that whole question. Okay, so again, you're just trying to find the right formula to get what you're looking for. If you're talking about, so in this first one, what's the maximum height that the ball will reach? Well, when you're chucking a ball up, when it's at its maximum height, the velocity is going to be 0. And we're trying to find the height at which the velocity is going to be 0. So that tells us we want to use this equation here, which relates the velocity to the distance traveled. For the second one, we're looking for a time it takes for the ball to hit the ground again. So we know when it hits the ground that the displacement is going to be 0. So we're using that to make an equation here. Then we're using the stuff we learned about how to solve quadratic equations to get an answer. And we're looking for which answer is sensible here. And in this context, having a negative time going backwards in time is not sensible, particularly because earlier in this situation, we didn't have the same acceleration. So this person would have been holding the ball steady before they threw it. And so therefore, we wouldn't have this an acceleration acting on this at that point. This downward acceleration would have been balanced by the force of someone holding this up. And so we can't use this negative time, can't go backwards in time. We want to use this positive. It's going to be the correct answer. That's when the ball's going to get back to 0. And then we've got our answer from that. And we just checked it by chucking it back into the equation. Make sure we haven't made any silly mistakes. Done. Next.